Hey everyone, it's Alfred.
Submarine.
And today's episode 203, and in it we're going to be interviewing James, who is the co-founder and lead mechanical engineer for Haddington Dynamics. So I'll give a little background on Haddington Dynamics, and then I'll leave it up to him to, I'll give a background on James, and then I'll leave it up to him to explain Haddington Dynamics. So James received his BSc and Master's in Mechanical Engineering from University of Massachusetts Lowell. His undergrad research, capstone project, and master's thesis all focus on the kinematics of robotic arms. A fun topic.
Complex.
Yeah, definitely. He joined Haddington Dynamics in 2016 along with co-founders Kent Gilson, Todd Enerson, and Christopher Fry. So without further ado, here's James.
Hi, James.
Hi.
How are you doing?
Good.
Good.
So I'm here in Las Vegas, where Haddington Dynamics is based. And so Haddington Dynamics, our whole goal is we want to bring automation to places it's never been before. And so to do that, we have one main product, and that is Dexter. It's a 5-axis robotic arm. You can kind of see a picture of it behind me there. So robotic arms can do like a lot of things. Basically, imagine what your arm can do. Now that's automated and written with code and can run 24/7 and basically be more precise and smarter than a human can be. So that's kind of what we're going for.
Yeah, no, that makes a lot of sense.
So how did you, like, your own personal professional journey to, like, leading up to Haddington Dynamics? How'd that go?
Right. So in undergrad, I did a bunch of research using robotic arms to do 5-axis printing. So there's like a ton of math involved there. And actually, I can show you a video if I can share my screen.
Yeah,
what we came up
please.
with. The idea was we 3D object, just like an STL, the same file like any 3D printer uses, and we try to project a 2D vector drawing onto that. And so that's really easy to design, but it's really hard to like manufacture. So I have a little short video to show you. Let's see. Go and yeah, right here.
Cool.
So this is my college robotic arm. I've had a few robotic arms over the years. This is a Stavely RX. It's an expensive robotic arm. It's industrial. It's not quite safe to be around. All metal. And you can see in this video, it's drawing just with an expo marker onto a 3D printed part.
Oh, wow. Okay, I see it. Cool. I was looking at the wrong spot at first.
Oh. So what's cool about this is it holds the object underneath a stationary tool. And so you can move between tools without tool changing and get multiple processes done. So you can see that's a nice straight line, but on a curved surface.
That's really cool. Dang, that's straight. Wow.
And was that using any active measurement, like CV or some sort of?
So that whole thing is open loop, and so we're not really getting feedback. There was actually, you can see in the video, there's a laser trying to measure the distance, the height. Okay. So I get like one feedback mechanism, but it's a 6-dimensional problem. XYZ, yaw, pitch, roll. I have errors in all 6 of those.
Right.
And so the master's thesis was focused more on like how do you calculate that error and correct for it. In which case I used cameras and got a 6-axis pose estimation and trying to cancel out all that. So lots and lots of math involved. I don't think there's any other way to do it. And basically all of my research kind of brought me to Haddington, which is making a robotic arm. And in fact, I even took all my MATLAB scripts and libraries and translated them into JavaScript, which runs on a robot.
Nice. That's amazing. MATLAB to JavaScript sounds fun.
Oh, yeah, you could say that.
Yeah. So
what's nice about JavaScript is it isn't extremely expensive. So
true. Yeah. And so expensive you meant actually monetarily. So that makes sense. For a second I was like, oh, process expensive, but I was like, wait, no, he means money.
No, it's pretty heavy process wise, and so is MATLAB.
Yeah.
But actually, that's a good segue into what is actually running on our robot. So we aren't running, the robot isn't running on JavaScript or C. It's actually running on an FPGA, much like what you guys do. But the difference is we're using off-the-shelf like AVNet board, but we wrote our own language to program it. That language is called Viva. It's kind of a graphical user interface where you're actually drawing the circuits in logic flow. And that was our co-founder Kent's previous company. He developed this language and sold off that company to fund this one.
Right.
So,
yeah, that's amazing. Like
yeah,
Viva is something
so that allows us.
Yeah. Go on. Like, we would just like tell us more about it.
Right. So that allows us to do really complicated behavior in an FPGA and still get like the really fast speeds. I mean, the speeds we're getting are comparable to supercomputers, and this is like a board that's on the actual robot.
Yeah.
So most robots have a giant crate. It's bigger than the robot themselves. That has like ASICs in it for each joint. It's like a huge card, for each joint that's a separate thing. But we compress that all down into like a little board that goes directly inside of the arm of the robot. Yeah, and so it's like a few different like benefits because of that. Hold on, I have a list right here. So we're able to get like extremely high precision out of our system, even though it's like really affordable and cheap. So a few things that make Dexter totally different than any other robot out there is the whole thing is 3D printed. So we're printing with really lightweight but strong material. We use a really special 3D printer called Mark Forge, which has continuous carbon fiber 3D printing. So it's not just like chopped carbon fiber getting mixed into the plastic and extruded normally. It's two different nozzles. One of them is like a nylon. The other one has an actual fiber that gets placed inside of the parts.
Wow.
And so with this, we're able to get like aluminum level strengths out of a 3D printed part.
Super cool.
And so that's just like one interesting design choice that we made. But all of these choices come from like the idea that we're using an FPGA. And so like the FPGA allows us to make encoders. This is kind of like the magic sauce is we have encoders on each joint. The encoders are being processed by FPGA, so we can print really imprecise encoders that end up being precise, which is kind of a weird thing. So we're 3D printing encoders, and that's normally like a terrible idea because the precision of the measurement is usually determined by the precision of the part. And if you're 3D printing them, precision isn't really there. So what we're doing is we're actually scanning over the encoder disk, measuring out the actual error and noise and all of that, and canceling it out like basically in real time with the FPGA. And to do that, we need like gigahertz or megahertz processing speed. So,
wow.
So, which is the tough challenge, and a lot of people aren't approaching robotics in that way. But so the question is like, what does that help you as a customer? Why do you care about it? And the reason is it makes everything cheaper and more precise. And so what we're able to get away with is we can 3D print parts. We can make really cheap, lightweight stuff that can actually flex, but we're measuring that deflection and canceling it out. And so we can use like really imprecise parts to get precise movement. So the end result is the movement of the robot is extremely precise, not necessarily the robot itself, the parts it's made from.
How precise
so
are
there's
you?
two kind of, how precise is it? That's a great question. So in each joint, we're getting about 0.8 to 1.6 million points per revolution. And so normally it's like the number of holes you have in an encoder is like the number of measurements you get. It's kind of a digital thing. It's either like on or off. And we're doing the full like analog spectrum between on and off. So it basically like you're shining a light through this thing and measuring how much light comes out. And if the light is fully through the hole, it's 100%. If you are half on the hole, it's 50. And then, a little bit more, 60, 70, 80, and you get like a whole like analog value out of it, which normally causes problems because you have to make that, a perfect sine wave for it to be useful, and get like precise circles. I can maybe show you a plot of that to make that make sense. But what we're doing is we're actually assuming it's not going to be a circle. It's going to be some, it could even be like a square wave and it would work. And we're just mapping. We're actually kind of generating the sine function rather than assuming it is a perfect sine function.
Yeah, like
if that
you're
makes any
fitting,
sense.
kind of. Yeah, you're fitting a sine wave to whatever comes out of it, kind of, right?
Yeah. Except it's not like we're fitting a continuous function. We're actually recording a lookup table for the sine wave, and then looking at the lookup table to do the inverse sine,
Gotcha.
or rather inverse tangent.
Yeah, that makes a lot of sense. So I mean, like, could you connect back most of your design decisions to that fact that it's an FPGA based robot arm, like other than the encoders and stuff as well, like?
Yeah, absolutely. So the precise encoders now allow us to do a few different things. So we can actually place these encoders outside of the motors. So most encoders like go on the motor shaft. And so most robotics rely on like the motor shaft angle before like the gearbox or the actual like, belts, pulleys, whatever transmission mechanism they have for the joint. The problem with that is like the belts, pulley, gearbox, all that stuff can flex and have backlash. A lot of gearboxes will have a ton of backlash, like almost a degree or two.
Yeah.
And you're not measuring that actual angle. So what we do differently is we put the encoders on the other side of the transmission. So after the motor shaft, after the gearbox, after the belts, pulleys, all that stuff, we're measuring the true angle of the joint, not where we think it is.
That's
so
amazing.
what's cool about that is the motors can skip, the belts can stretch, like all sorts of problems can happen, and we're still measuring exactly where we are and correcting for when we're not there.
Wow.
So because of that,
So
if something skips or whatever, you can always go back to home. Like,
yes. Yep. And so another interesting design choice is we didn't use servo motors. We're not using DC motors. We're using stepper motors, which is weird. Most of the time you would not use stepper motors for something like this.
Yeah.
But what a stepper allows us to do is we can get a rough estimate of the angle before the gearbox, belts, and transmission, all that stuff, and after. So we get two different angle measurements for each joint.
And then common filter it.
And then what?
Common filter.
Yes, you could do that. But actually what we do is we measure the difference between the two of them, and that correlates to a torque.
Oh.
So with the same really precise angle measurement system, we're also getting a really precise torque measurement system.
oh wow,
Very cool.
Which is interesting. And so this is all kind of assuming like Hooke's law, like everything is linear elastic.
Proportional.
So
yeah.
if I stretch the belts by like 2 degrees, and I know that the stiffness of the belts is like 4 Newton meters per degree or whatever that number is, I can calculate the actual torque, the true Newton meter torque coming out of each joint, just by the position difference between the two measurements.
Yeah, I love how
so that's
like the things you're saying are things people learn in fundamental physics and never realize how they can translate into robotics. Like, yeah.
Yep. Oh, I think that's the coolest part about this project is like a lot of my schooling is actually being used, which I feel like is such a rare thing.
Mm-hmm.
So all the kinematics, all the math, all the torque stuff, all the physics, like that's how you run robots. It's really, there's no other way to do that.
Yeah.
Unless you really brute force or use machine learning, but even machine learning won't give you as good results as like actual solved continuous functions.
Exactly.
So.
We actually already have a question in the chat if you want to take it. So this is actually one of our team members. He asked, like, you won the Hackaday Grand Prize, so you're a big fan of open hardware. How much of Dexter is open?
Right. So all of Dexter HD is open source. So all the 3D printed files are online, all the FPGA code. We have actually a C firmware, like every software and hardware is online. Other materials of things you have to buy. There's a few things that we make our own PCBs, so you have to buy like an electronics kit from us, and you can see the details of that in our store. But everything we do, we want to keep open source.
Super cool, yeah.
So how long would it take somebody to build this if they wanted to, like in their garage?
Right. So I guess first of all, it takes about 13 days of print time to print the parts for this.
Like continuous print time.
just the print time alone is like 13 days. But what you can do is, I mean, what's really cool about 3D printing technology is you can break it up. If you have 2 printers, you can cut that time in half.
True.
Or more. So we actually have like 13 printers, so we're able to print a robot a day.
Nice.
And then, if we wanted to, double our production, all we have to do is double our number of printers, and then we're printing twice as many robots.
Yeah.
Wow.
It's a really scalable thing. So that's kind of like there's a lot of benefits to like 3D printing manufacturing wise. If we find a bug in the hardware, we can fix it and then put it into the pipeline the next day, and then it goes into all the robots from then on.
Right.
Which is both powerful and dangerous, because we definitely have made changes that were improvements that actually made things worse.
Oh gosh.
So, double-edged sword.
Yeah.
No, that makes sense. So, speaking of like, software and like, how you use Viva to program it, like as a user who's trying to program Dexter, like, do I need to know programming? What environment am I going to use? What does it look like? All that stuff.
Right. Okay. So there's a few different ways to program Dexter. The dead nuts easiest way to do it is this thing we call a GUI, which is a physical user interface, rather than a GUI, which is a graphical user interface. And so the robot will boot up, and all you have to do is like tap its head, drag it through the motion that you want to record, and it'll play that back. And so there's a lot of really simple things you want to do, like, hey, I want to like pick something up from here and put it in here, and I just want to do that all day. And that can be done, in 30 seconds of just booting on the robot, going through the motions and playing it back. I guess first I should probably mention that because we're measuring torques, we're able to have a haptic robot. So we can measure the torques when you're holding it and pulling it, and move with the forces that you're applying. So you can grab the end of it, and it could feel like a limp robot, like the motors are off, but they're actually actively on and compensating for the forces that you're applying. And so what's cool about that, rather than shutting the motors off, is now you can like cancel out gravity. You'd have a really heavy arm or really heavy thing you're picking up, and it can measure those and kind of remove them. It's like the same algorithm as an export.
Right.
Although right now I should mention that our robot can only lift about like 3 kilograms. So it's still weaker than a human. I know a lot of people expect robots to be like super strong or whatever. But for us, it plugs into the wall, so it's like super low powered. And it can't lift like super heavy things, but 3 kilograms, about like six pounds, is more than enough for like most projects that we attempt.
Yeah, no, that makes sense.
What would be the limitation there? The steppers, the materials?
Yeah, actually, the materials have never failed, as far as I know. So because we're using carbon fiber for everything, like that's super, super strong. The stepper motors are still the weakest link in terms of like torque capabilities. What's interesting about steppers is their holding torque is much higher than their moving torque. And so we'll be able to hold things, on a much higher payload. But as soon as you start, I want to lift things, that's where you get like sort of issues. I should also mention that it's not just a straight stepper motor. We're using fancy gearboxes called Harmonic Drives, or rather that's like the Kleenex version of them, where they're actually like wave drives. They use like a flexible gear that actually flexes and walks around a stationary gear. They're super cool. I never heard of them until I worked on this project. But you're able to get like really, really high gear ratios in a really small volume. So we're getting about 50-to-1 gear ratio, and the thing's only like this big.
That's amazing.
Wow.
Yeah. I mean, I gotta say, like, one of the things about Dexter when I first saw it that, like, completely blew my mind was, like, if you pushed it or whatever, it would still come back to, like, the spot it's supposed to. Right.
So that's the magic of the encoder system, is it's closed loop. So, like, you could, train the robot to do all this stuff, and then you could do it, and it'll hit all the points perfectly, no problem. And then you could put a weight on it, a load on it, and it will still hit all of the points the same way. Even though the belts are stretching, the motors might even skip, who knows, it will still get to exactly where it needs to go. And by the way, our precision is about like, it's incredible that we're doing this with 3D printed parts, but like 0.005 0.005 millimeters of step size, and then 0.05 millimeters of precision. So like every time you get that point, you'll be within 0.05 millimeters, which is more than enough for most applications.
That's amazing.
Damn.
Yeah. In
And
fact, the torque sensors are just as sensitive. And so we were actually messing around by throwing like a cotton ball, and we were able to measure the force of the deflection of the beam from the impact of the cotton ball, which is just
Wow.
like, you can't even feel that yourself, you know?
yeah.
That's crazy. Wait, so you have torque sensors on there?
Yeah, well, inherent torque sensors. It's the same encoder system.
Right. So yeah, like not like off-the-shelf torque sensors or anything. It's like the
No,
math.
it was the
torque
subtraction
sensor.
of
Yeah.
the difference. Yeah.
Yeah. So it's just kind of like inherent to the system that we already have, which makes it much more easy to build and cheaper. Most of the time you put like a force probe on the end of the robot, but we can actually take the torques from like joint space, so that the torques in each joint, and convert it into like an XYZ like vector on the tip of the robot. So you can be like measuring loads, in XYZ space up here, even though the robot's this big polar mess mathematically.
Yeah.
Super
And
cool.
since the sampling is so fast, like if I were to touch it, it would know I'm touching it before I know I am, right?
Before you do. That is correct. Yeah. So we actually had someone who was a brain surgeon come in and try to have a competition with the robot. See, if he could touch it before it could feel him, or if he could feel it before it could feel him. And I think he won maybe once out of 10 times.
Oh wow.
So,
Dang.
which is pretty incredible. And so like, what does this really mean in terms of like capabilities of the robot? One big thing is like your positions will always go back to like exactly where they need to be every time, which is something you expect robots to do, but they won't necessarily do that. The other thing is the step size is so small, you can actually do small scale projects, including movements, but also really small courses. So we did a demo where we actually put a microscope and a laser on the end of our robot, and engraved grains of rice. So we couldn't really see what we were doing without the microscope, and so we could actually go down, look at the grain of rice, and move the robot around, and like write words on the grain of rice.
Oh my god.
I guess something I should have mentioned this before is you can drag the robot through its motion, record and play it back, but you can also project that onto other robots. So drag one robot over here, and then another robot will have the identical position of their controller.
Right.
But then what's cool about that is you can edit it, so you can scale it down. Like say I move a meter up here, it moves like a millimeter down there. And so when you're looking under the microscope, you can do like large human motions, but it's really only moving like a couple, fractions of a millimeter.
Dang. So with all of
Which,
this, wouldn't this be better than like the Da Vinci surgical robots?
Potentially. However, I do have to say we are not FDA approved.
Yeah. With that big
Yeah,
exception. But
Yeah.
wow. Okay.
We actually have another question in the live chat from Philip.
Okay.
He asks, what about harmonics and nonlinear responses depending on speed?
Right. So the control system is closed loop, so eventually it will get there, but it kind of limits on like how high frequency will it get there. And so if you have something vibrating, like we're going to try to sit there and compensate for that vibration, but we might end up like hitting a harmonic and totally going, amplifying that. And I think we were saying something like 40 hertz, up to 40 hertz. There's somewhere around there in terms of control. We actually did set up a demo where we put a piece of sandpaper on the end of the robot. And because like the FPGA is going so friggin' fast, we were able to vibrate that sandpaper back and forth fast enough to actually sand stuff. And this isn't like using an external tool. We're just using the joints that are already on the robot, just sitting there vibrating.
That's so fun.
In fact, I'm sitting on a table right now that has some sanded off spots on it.
That's hilarious. Wow. So like, what are some like use cases, like applications that you've seen so far, or that you foresee also in the future?
It's so far, and I should mention, so far we sold about like 300 robots. So there's like 300 robots out in the field right now, and it's all over the place. We never really expected any of these. You can't even imagine like what you can do with a robot. Yeah. And so we have people like on the super high end, like NASA has a few robots. They're using it to actually detect like fractures and drone wings. And so like you can actually feel better than a human can and detect little tiny bumps. And that's a big problem if your propeller is cracking. It's about to fail and the whole drone's going to crash, and that's something you don't want to happen.
Yeah.
So there's that, and there's also like the biomedical field. There's a lot of people doing like research projects. There's a professor at New York Institute of Technology, Alex. He's using it as a bioprinter. Basically, he's trying to use the small motions, take advantage of the really small movements the robot can do, to print kidneys with little tiny like globs of cells. I don't think it's quite cell by cell, but it's like tens of cells, and he's just placing them in this fluid, and he can use like the 5 axes of the robot to place it exactly in where it needs to go without disturbing the rest of them, and kind of like grow the kidney from the inside out. And so those are all like the really high end. They have a lot of money, a lot of research stuff, but there's also like really low end stuff. A lot of like small businesses that would never think to automate. We had someone who was interested in tuning pianos, just having a robot sit there, hit the key, listen to the tune, turn a knob, sit there, hit the key, and just, feedback loop of tuning a piano.
That makes a lot of sense.
You never see like robots in that space.
Yeah.
Or there's another customer who was taking muffins. They had a machine that was making muffins, and they had a bunch of trays they wanted to put the muffins in. Just like super simple, grab the muffin, put it in the tray. And that's like the type of thing that's really easy to train by hand, but not super easy to just like type in numbers and trial and error.
Yeah.
You do that once and just have to play back.
Right.
And by the way, that's the namesake of the robot, is we're capturing human dexterity into software, hence the name Dexter.
Nice. Yeah, that's really cool. I think like what's nice also about Dexter is it's so easily reconfigurable that like say I have it in like my ice cream shop or something, like I can have it do multiple things at different times, like different things at different times a day, like because I just have to reprogram it and it takes like a couple minutes. It's like super easy.
So actually it's funny you mentioned ice cream. So we were working with a client that we could use a robot to not only serve ice cream, but also sit there and clean the machine when it's done.
Nice.
Yeah. And so I should talk about like how you program it besides the training by hand. So we have an API it's a TCP/IP socket, so you can send like any sort of string from any programming language. So like C++, we have Unity, JavaScript, and Python, anything that has socket interface. In fact, we even had a client. This is kind of a cool open source story. We had a high school student develop a Scratch interface. Scratch is like
nice.
It's like blocks programming for kids. I don't know if you're familiar with it.
Yeah, for sure.
So it's like this kind of kids like block programming language, and he was able to actually like drive the robot around using like commands that he wrote in that language. So any language you want, but we also do have an integrated development environment we call Dexter development environment. It's kind of the same idea as like Arduino, where you have like a really simple like application you can download. It'll just like work out of the box. You prototype your stuff in that, and then if you really want to make like a commercial application, you might switch over to a different programming language that you're more comfortable with.
Right.
But our IDE makes it like super easy to learn how to program Dexter. So it has all like the libraries, the kinematics, all the stuff you need to know about like our specific robot, like built in, already preloaded into the language. In fact, I can almost give you a quick demo of that.
Yeah.
I got to see my mess. So this is DDE here. And what's super cool about DDE is because we like made it ourselves, we can kind of control the whole environment. So you can go through and do things like this. I can click on keywords, and it actually can give me help on those keywords. And you can see like on the right here, all the help is built into the environment. So all you have to do is like click on like, hey, what is Dexter? And it'll scroll and tell you exactly what like that variable is, or the class, or whatever information you want to know. And then what's cool is like even if you don't know JavaScript, you can click on JavaScript, keywords like var, for example, and it'll bring up like the actual like documentation on this kind of
Very nice.
code. And so like our whole goal is to make it like as easy to use as possible. because that's how we bring automation to places that's never really done it before. You know, we don't expect like engineers to be the sole customer of this. We want like everyone to be able to use it.
Yeah. That makes a lot of sense.
Yeah.
So it's so the IDE is JavaScript, just vanilla JavaScript.
It's in JavaScript. Yep.
Okay.
Yep.
Cool. And then when you
which is cool. You can actually download like Node libraries too. You know, so anything that's out there, you could just like pull in and use. So.
Nice.
And then, like, if you were using a different language, say, is there, like, how do you load your program onto the processor? Like, is it, like, does it have, like, a command line, or, like...
There are two kind of motifs in programming Dexter. One of them is you have, like, a computer as, like, the main brain of it, and it's just sending commands to the robot. And that's really useful for prototyping and debugging. And then what you want to do when you're done debugging is send off your, we call it jobs, or like, you know, the script for the robot onto the robot itself. So far, we've only done that with our integrated development environment. So we actually have that running on the robot in a Node application. And so what you do is like you could just save a file and just copy it over to the robot, and there you go. Which is a little different than our Arduino, I guess.
Yeah.
Yeah, but straightforward, easy.
Yeah.
Yeah.
Awesome.
I should mention that all the documentation for that is on our GitHub.
Okay.
Where we have a Wikipedia with like, you know, every sort of bit of information you could possibly imagine.
Yeah, our software developer will love how well documented all of this is.
Oh, okay.
Yeah, he
we'll
loves
see.
documentation.
Yeah, we'll see about that. Yeah.
Yeah.
Okay, I have a couple of demos I can show you guys. If
Yeah,
Yes.
please.
Let's see. I need Ken. So I will change my camera over to this thing. Change my camera.
You ready to show?
Yes. All right, so I should be on a different camera now.
Yep.
Oh, sorry.
So let's see. Hold on a second. I need to go.
Somebody had asked if it can lift an egg. I'm pretty sure it can. It can.
Lift a what?
Lift an egg.
Oh, yes, totally.
Pick and place
you
machine.
could think of like,
definitely.
yeah, 1 kilogram is about like a bottle of water. So like 3 of those, that helps.
Yeah.
Yeah, and it's so, like, if it's so sensitive that it can tell that you're touching it before it touches you, it can
Yeah.
probably lift, like,
Yeah,
crush
it's
an
really
egg.
important for
Yeah.
eggs. You know, you don't want to crush an egg.
Yeah. And since it can
right.
sense you so quickly, it'll like it's safe to be around then.
Right, so that's a really cool thing
Whoa, is this camera on Dexter by any chance?
about torque sense. Hit someone that. Yeah. Okay, so can you see that camera?
Yeah.
It's looking at something, I don't know what it is right now, but
Like the table?
I guess. Yes, the table. Oh, I see. Oh, so this is the point of view of Dexter.
Yeah, so this is actually on a
Cool.
Dexter right now.
Oh my
This is so
god.
Right. And so I'll give a demo of that later, but I guess right now we can show, we have a demo of the tool changer setup, which...
Sounds like the future.
Oh, perfect. Okay. Yep, so here we go. So we're going to have one Dexter being the film crew and the other Dexter showing the demo.
This is amazing.
This is great.
Yeah. As you see, it's dipping into a tool. It's picking up a probe here. And this is like a VNC. So this would be hooked up to like an oscilloscope, taking like electrical measurements of, we have like printed conductive circuits here.
Nice.
Yeah, we can move that around. Yeah, and so when it's done with taking measurements, you can put the tool back and pick another one up to do a different process.
Nice.
Yep.
So Dexter can be used in like a mini mill or like probably like things like that too.
Yeah, and anything.
Right.
Basically.
I guess I should mention it does have the actually I solved the inverse kinematics of this, so you could work in XYZ, pass a G code, and it'll just play it back.
Whoa.
Oh.
Like a mini.
So Dexter can 3D print itself.
Yes and no. We've been so close to having 3D print, we just actually haven't put an extruder on it yet. In theory, yes. Yep, there it goes. Yeah, and then I think we have another demo. Alright, so I guess we should take a look at Dexter.
Oh, there we go.
Ooh.
Are you trying to control the camera crew, Dexter, like manually, real time?
Yeah. I am. It's a little tricky. I'm actually using an Xbox controller to control it.
Oh, nice.
Oh, wow.
Which is a little confusing. I can show a video of that in a second. But we also have another demo set up to measure torques, just to show the torques off. Let's see. Oh, is it unplugged? Yeah. All right. Put that in. So I'll give that a shot. There we go. Let's see. It might be easier. I don't know if we can do this in 2 shots. When I share my screen, does my face show up?
We don't see any change yet. We're still on the Dexter camera.
Yeah.
Right.
Well, I have this pin. Well, there's nothing to pin right now. So you only pin when it's the sharing screen. Yeah.
Got it. Oh. Okay.
Okay. So now
so
we
you
have
can see my
both.
screen.
Yeah.
And so I'm going to run Torque's job. And so you can see down here, it's spitting out some numbers. And I wish I did a graphical view of this, but so those numbers represent the unit vector for the direction of the force applied to the tip of the robot.
Nice.
Yeah, and I don't know if we can get a shot of both, but John's going to like push up in the Z direction on the robot, and you can see that this is giving us a positive like force vector in that direction.
Okay.
Down. Yeah, let's see if I can get a video of what he's doing.
You're doing great with all these transitions.
Yeah.
I know so many transitions. Back to this camera.
Yeah, but you'd need that special printer with the carbon fiber, or else it wouldn't be as nice.
Yeah, Mark forges are amazing. Like even just like the quality of the parts without carbon fiber in them is like way better than anything else out there, at least for this price range. Let's see. Okay.
Oh wow.
So
nice view.
there's John, if you could see him.
Yes.
And he's
Hi, John.
He's pressing on the tip of the robot, and so the direction that he pushes is actually like we can measure that and compute it, which you can imagine is a really like useful thing on a motion platform. You can move down until the force vector is pointing up, or in other words, until you hit the table or the thing you're trying to grab. You can move the robot around and measure the friction while it's moving. And that's really useful for things like, say you're cutting paper with a knife, or, or maybe you don't want friction. Maybe you want, move until there is friction. Just like this basic sense of torque and force, like opens up a whole world of things you can do. So, yeah.
All right. Well,
That's
Wow.
basically
cool.
it. Yeah, thanks, John.
Love how, like, I don't know, like, when you think robots, you think, oh, it needs sensors to know what's happening, and, like, encoders are sensors in a sense, right? But that's the only
Yeah.
thing you're using. You're not using anything else. Like, I don't know. It just
Yeah.
kind of blows my
There's
mind.
no fourth probes. Yep, we're doing a lot with one sensor.
Yeah, with one type of sensor. It's
One
crazy.
type of sensor.
Yeah.
But I should also mention there are USB ports on the robot, and so you connect a bunch of like serial devices to it. So we've done that with like Arduinos. You could put like anything in Arduino and then just like plug the USB into the robot. If you want like light sensors, sound, whatever. But we've also we've been really successful with a camera called OpenMV. It's similar to like OpenCV, which is like the whole library for vision system. OpenMV is cool because it's an integrated like camera with all the machine processing, all the machine learning,
On device.
vision processing on the camera itself. And so what's cool about that is it can look at like faces and compute like the XYZ of a face and just spit it out to the robot, and it's not slowing anything down.
Right.
Which otherwise is a fairly complicated thing. And it's just like this prepackaged thing, and it comes working out of the box. We use it a lot for something called April tag tracking. So April tags are like really simple QR codes, and you can put an April tag on something, and from a single frame, you can get like the X, Y, Z, and the yaw, pitch, roll out of where that April tag is.
Whoa.
And so this is really useful because you can put that on the thing you're trying to grab or the fixture you want to put things in. And those move relative to the robot, but the robot can still find out exactly where that is.
Those are the types of tags you see like in Boston Dynamics videos where they have their robots
Exactly.
picking up stuff.
They have them on like the cardboard boxes, like blown up, and it's probably one of the best ways of doing that simply.
Cool.
Yeah.
Wow.
Just so many amazing things. Like,
Yeah.
Yeah, we are a little envious of Boston Dynamics because our name is Haddington Dynamics. It's kind of the same idea.
Yeah, but I mean, you have like your whole different avenue that like that's just like a different area of robotic revolution, I think. When is there going to be a commercial, smaller version that people like us can purchase?
or build.
Right.
Or build.
And so we've kind of almost adopted this model that like Tesla has done, if that makes sense, where they started off with a really high-end product and used that extra margin to develop the product, pay the engineers. So right now, a lot of our costs aren't in materials; it's in like the engineering labor because we're still developing the product.
Right.
And so I hope that like once we have the thing figured out, like the cost of materials isn't that high. I think we can start, really driving down the costs.
Right.
And like eventually, like lowest of the low, we could probably get this under like $1,000 maybe.
Whoa.
But there are a few things that we do want to do to get there. A really cool method of having the whole robot be printed and the robot being a 3D printer is you can have the robots start to build themselves. So the robot can 3D print the part, pick the parts up, and then assemble the parts.
That's
and then
crazy.
your cost of labor is zero. There's going to be energy, but
Yeah.
You could 3D print it.
In
It
fact,
can be
we've
the pick
already,
and place.
So once we hit that point where the robots are making themselves, that's game over. Robots are going to take over the world at that point.
Yeah, I mean, wasn't that in one of Isaac Asimov's books or something? I don't remember, but something about self-replicating. Like once you have a self-replicating robot, like that's it. That's the end. The end of the world.
Yeah, but on the other side of that, potentially once you buy one robot, you purchase it, maybe take out a loan like a car if it is expensive. I don't know if it will be, but once you buy one robot, you can have it make a whole army of robots for yourself. So imagine instead of buying like $100,000 like robotic arm, metal giant robotic arm, you buy like one of these and then like print out a bunch of other ones. And then you can kind of do things in parallel, the same way we're doing like the printing in parallel. You could break up tasks and do them all at the same time. That's not necessarily like one really expensive thing doing the task.
Yeah.
For example, like picking up eggs, you could have like one robot doing that and, waiting on the finish one task to go to the next, or you could just have a whole army of robots just sitting there doing it constantly.
Yeah.
That makes sense.
Super cool.
Yeah.
So since it's all open source, would it be possible for somebody to miniaturize it if they wanted to and bring the cost down?
Right. So realistically, the way we have it set up, the costs are kind of fixed. And so even a smaller robot, well, I guess that's not true. So I guess the real costs come from the FPGA, the harmonic drives, and the carbon fiber parts. So if you made it smaller, you'd probably get rid of a lot of the carbon fiber parts. You could probably go to like lower gear ratio harmonic drives, but the FPGA would have to stay the same.
Okay.
Because you really do need that high frequency measurement system. I mean, you could make something that isn't a Dexter for much cheaper. Not the precision, not the feedback loop. So it should be possible to make an open loop kind of like inaccurate robot for pretty cheap.
Yeah.
But I don't think we're quite there.
Okay.
Yeah, that makes sense. So this has been really exciting, and like it's been great. Like I think we covered most of the questions we had.
So too, plus more.
Plus more, yeah. Is there like anything else like you would like to share with like just in general before we wrap it up today?
Yeah, I guess some other things, like we're not just creative on the mechanical and the engineering side of it, we're also kind of creative on the business side of it. So you don't have to necessarily like own a robot. So we're talking about different business models where you like rent one for a month or you lease one.
Wow.
And which make more sense for a lot of like small businesses or just average people. And there are like different ways, because like you can remote into a robot, by the way. So we're talking about having a robot set up in our office. You can just like prototype your stuff, get all your code working, and then you rent it for a little bit or something like that, trying to make it really, really easy and affordable for those people.
Oh, that's such a cool demo.
Super interesting.
And just use case.
Yeah, also like if you could lease robot arms, people could lease robot arms for when they're going to conferences and they need like something to happen, or I don't know, like
right.
If you that's actually
in fact,
very
that's actually a fairly large market, is just random companies asking us to bring a robot to their booth.
Yeah.
And just have it move around and attract customers and like not really do anything functional besides that.
It's true. I mean, especially places like CES, there were so many robot arms that were there not for the sake of them being robot arms, but for the sake of attracting people to their booth. Like it's not like the company really cares for robot arms. Like they do something else.
Or it could be operating a demo for the company instead of having a person there. Right.
And that actually is kind of our dream, or at least like the transition from human labor to completely robotic labor. I think, what's the saying? We have a saying called like human, let's see, on the loop. So human on the loop, in the loop, and out of the loop. So basically like you're remoting into a robot to do the job you're already doing, say like a construction worker. And you're remoting into a robot and having it nail something down, and you're still getting paid to do that, just the robot's doing the actual physical labor, and you don't have to physically be there.
Right.
So it's like direct human control. And then the next stage of it is like the robot it's learned from the recordings you've done, because we can capture all of that data that you sent to the robot and map it to like the camera that you're looking through, and then the robot can learn how to nail things itself. But you will probably still want to like watch it, make sure it doesn't like screw up, and remote into it for like corner cases, like say it dropped it or something, you go pick it up and put it back in.
Yeah.
And then once you get that data, then you get up to the really high percentage of success, and then it's completely autonomous and no one has to work and robots do everything. At least that's kind of our general dream.
Trajectory. Yeah.
That's really funny. Thank you for sharing the business model thing. That was not a question we had thought to ask at all, because we had no idea that like you were thinking of like other ways of making it accessible for people. Yeah, that's super cool.
And sorry, in that same vein, there's two other like interesting business things we've done. We sell this thing called a making vacation. So like if you want to buy a robot, you can come out to our office and actually like build it yourself.
Super cool.
And so because like a lot of our costs are in labor, you become like the labor, and it ends up being a little cheaper than
Yeah.
just buying the robot outright. So, but it's also really cool because you get to like hang out with us, and we always like love hanging out with cool robotics people. It's never gone wrong.
Yeah.
So that's always a good time. So that's one of them. And then the other thing we do that's interesting, we sell micro factories. So not only just the robot, you can actually buy. We have like a set of software and manuals and just our time, and we help you build Dexters yourself, and you can sell them for whatever price you want. We get a little cut of that, but otherwise, like it's your factory, it's your company selling our robots, building them yourself. And so there are people who are looking at us trying to like, just have a few 3D printers in the garage and just like make money building robots on the side, or so.
Yeah, I mean, I can see how somebody who like is a robot enthusiast or just in general like loves 3D printing or something could totally do that without like too much like hassle and make some. Yeah, that's interesting.
Right.
Very interesting.
I mean, even if it's like you buy the 3D printers and just print the parts, don't even assemble them. Like we'll buy them back, because right now it's like the 3D printers are kind of limiting us into like production speed. So our goal is kind of like distribute this manufacturing, not centralize it.
Yeah.
Which is like a really big motif of Industry 4.0.
That makes a lot of sense.
So, I don't know. There's a lot of cool stuff going on here.
Yeah, no, for sure. Curious, because somebody just said regional Dexter or Dexter to Dexter Europe. I don't know if this is what they meant, but also just the question popped into my head if like you've shipped internationally or like if there have been use cases internationally. Yeah.
We're all around the world. We do have a bunch in Europe, a lot in Germany, England, I think one in Spain. We're all over like Asia too, and Hong Kong, Japan, Singapore. Yeah, we have a lot of robots in Singapore actually.
Very cool.
But we are going to like international trade shows too. So I think we're going to be in Munich for a show called Automatica in August or June, sometime this summer. We're going to a trade show in Japan in a couple weeks.
Nice.
And then there's another show in Korea. So we're definitely looking at like the worldwide market.
That's awesome. Yeah, because I mean, there's no region for robots. It works everywhere.
Right.
Yeah.
Yeah.
That's awesome. All right. Well, this has been really fun. Like, anything else that we've missed that you like? Just because like you came up with something that we hadn't thought of. I'm like, oh, what other interesting things have we missed?
Right.
Also, no pressure, because we'd love to have you all back at some point as well. But yeah.
Yeah.
Awesome. Well, I guess with that, unless somebody in the chat has something, we'll give them a couple seconds.
Yeah.
Yeah, I mean, it's been super cool.
I should mention we have a company Discord, and maybe we can post a link in the description if I can get you guys a link.
For sure.
And we like all of our engineers, our whole team is like on there 24/7 basically. And so like if anyone has any questions, like we can respond right away. It's been really successful in people in terms of people who have robots, because they can ask a question like, hey, how do I spell this function name? And we can like answer it immediately. It's not like you're searching on Google and can never find the answer. Like we're super available all the time. Yeah. And we're like way into this too, so it's a lot of fun for us.
Cool.
Yeah, we'll definitely put it in the description if you send us the link. And somebody was like, Dexter solving a Rubik's Cube, 2 Dexters.
Wait, I should mention that. We actually I have it right here. This, we made a Rubik's Cube. We've already thought of this. So this is the Rubik's Cube we actually made, and we cut out little stickers. And these are little April tags. And so the idea is you can have the Rubik's Cube, like at all some weird angle, and the robot can actually use the OpenMV camera and find the actual like XYZ positions of each face and which color it is. So that's on the way. We'll have a cool demo video coming up soon.
Amazing.
Cool. I'll be waiting for that.
So excited. Awesome.
Well, thank you, James, for coming on. This is amazing. My mind's blown.
Every time.
Yeah, every time. So cool. I want to build one so bad. One day.
Yeah.
All right.
Awesome.
Well, we'll speak again soon. Thank you for joining and, explaining so much so well to us. Feel like I understand a little bit better, like how the, robot is working, the encoders, the torque, the math, crazy. But yeah, so thank you for coming and we'll see you next time, hopefully.
Yeah.
All right.
All right.
Thanks for having me.
Bye.
Bye.
All right. And then going back to here.
I'm just mind blown again.
Again.
Yeah.
And again. It always
we
happens.
first met them at the Bay Area Maker Fair last
Yeah.
year. You met them at CES.
And I went to their office.
Which I'm so jealous
Yeah,
of.
it was amazing. It was
my
nice.
God. Yeah.
Very cool.
Just so cool. I could dig into this for so long. I
Yeah.
mean, when we were at Maker Fair, we spoke for I don't know how many,
I don't know.
several
We just
hours.
stared at Dexter for a couple of hours.
Yeah. It was a lot of fun.
Yeah, no, it was. But, if you are interested in, like, what Haddington Dynamics does or checking out some of their robots, checking out, like, their code, all of it is, like, on GitHub, as far as I can tell. So we'll put links to all of their resources in the description. Check them out. Feel free to ask questions. We'll pass it on to them / put it in their chat that we'll link soon as well. But yeah.
That's it for this episode.
Yep. Thanks for watching.
Yeah. Bye.
Bye.